In the desert of southern Washington state, there is a machine the size of a house that has one rule above all others. It must never be allowed to go cold. Inside it sits a pool of molten glass, glowing at over 1100 degrees. Not glass the way you know it. Not a bottle. A living pool of it, orange and slow and heavy, held in a steel and ceramic box that weighs 300 tons. And the people who built it, and the people who run it, are united by a single fear. If that pool of glass ever freezes solid, the machine is dead. Not broken. Not in need of repair. Dead. A 300-ton block of ruined stone and trapped glass that may never run again. That sounds absurd. Glass is one of the most ordinary materials in your life. It is in your windows, your phone, the jar in your fridge. It is cheap. It is everywhere, and it does not seem dangerous or delicate or worth a moment's thought. And yet the furnaces that make it are among the most unforgiving machines in all of heavy industry. Machines that run continuously for 10, 15, sometimes 20 years without ever once being switched off. Not because someone forgot to turn them off, because turning them off destroys them. Tonight we are going to work out why a machine that melts the most common material on Earth is one of the few that can be killed by the simple act of stopping. Why glass, specifically, is more dangerous to its own furnace than molten metal is to a smelter. And why, in that Washington desert, engineers have bet the cleanup of America's worst nuclear waste on a machine that can never be allowed to rest. To understand it, you have to start with something strange about glass itself. Most materials have a clean line between solid and liquid. Water freezes at 0 degrees. Below that, ice. Above it, water. Iron melts at a specific temperature and turns from solid to liquid at a definite point. There is a threshold, and the material is on one side of it or the other. Glass does not work like that. Glass has no single freezing point. As it cools, it does not suddenly snap from liquid to solid at one temperature. Instead, it gets thicker, and thicker, and thicker. It moves from a runny liquid to something like honey, then to something like tar, then to something like cold toffee, and finally to a rigid solid, all across a wide range of temperatures, with no clean line anywhere in it. On the way down, it passes through a state where it is neither properly liquid nor properly solid. It is just monstrously, increasingly thick. And that in-between state is the trap. Because a glass furnace does not just hold glass, it holds glass that is flowing. Raw material goes in at one end, molten glass comes out the other in a continuous river that never stops moving. The whole machine is built around that flow. The heat, the shape of the tank, the way the currents move through it, all of it assumes that the glass is liquid enough to move. Now imagine the temperature starts to drop, not to freezing, just down. The glass gets thicker, it moves slower. And here is where glass turns on its own machine in a way that metal never does. In a copper smelter, if the metal starts to solidify, you have a frozen mass, but copper is a clean solid. In principle, you can reheat it and melt it back. It is a setback, an expensive one, but the metal is recoverable. Glass, when it thickens and cools in place, becomes something far worse. It turns into a rigid, glassy, stone-like mass that fuses itself to the walls and the floor of the tank. It grips the refractory. It fills the corners, and critically, reheating it is not a simple matter of melting an ice cube. To melt that mass back, you have to bring the entire structure back up through the exact temperature range that cracks it, with a solid block of glass locked inside, expanding and pushing against walls that are trying to move at a different rate. Very often, the tank does not survive that. The glass has effectively welded itself into the machine and taken the machine with it. This is why glass furnace operators are afraid not just of off, but of slow. The furnace must not merely stay hot, it must keep flowing. If the flow stops, even while the furnace is still warm, glass begins to freeze in the corners of the tank, in the throat, in the dead spots where the currents are weakest. It creeps inward from the edges, and once it has a foothold, it is extremely hard to get back. So there is a rule you will hear in the industry, and it sounds insane until you understand it. When a glass furnace has to slow down, because equipment downstream is being repaired, because there is a problem on the line, they do not stop the glass. They keep melting it, and they keep pouring it out, and they dump the perfectly good molten glass into a basement where it is cooled with water and carted away as scrap. They will make glass that no one will ever use and throw it away by the ton, hour after hour, purely to keep the river moving so the tank does not freeze from the inside. Think about that. The furnace is so afraid of its own contents solidifying that it would rather waste everything it makes than allow the flow to stop for too long. Producing garbage is cheaper than the alternative, and the alternative is the death of the whole machine. And this is before we have even talked about what the glass does to the furnace while everything is going right. Because molten glass, like molten slag in a smelter, is corrosive. At 1100 to 1500 degrees, it slowly eats the very walls that contain it. The tank is lined with special refractory blocks, often a fused material made from alumina, zirconia, and silica, chosen precisely because it stands up to molten glass better than almost anything else. And even that is on a countdown. The glass attacks it. Alkali vapors rising off the melt attack it from above. The worst wear is right at the glass line, where the surface of the melt meets the wall, and at the throat where the glass flows through, the places where the moving glass scrubs hardest, so the lining wears, slowly, predictably, unavoidably. And there is a detail in how these furnaces stay hot that is worth pausing on, because it tells you how hard people have worked to keep the fire alive as cheaply as possible. A big glass furnace does not just burn fuel and let the heat escape up the chimney. That would be ruinously wasteful over a decade of continuous running. Instead, many of them are built to breathe. On each side of the furnace sit huge chambers packed with a lattice of special bricks called checkers. The furnace fires from one side, and the burning gases sweep across the molten glass and then pour out through the chambers on the far side, dumping their leftover heat into that brickwork on the way out, heating the bricks until they glow. Then, every 20 minutes or so, the whole furnace reverses. It stops firing from one side and starts firing from the other. Now the incoming combustion air is dragged through those preheated bricks first, picking up all the stored heat before it reaches the flame. The furnace is, in effect, breathing in through a set of lungs it warmed up on the last breath out. That reversal happens around the clock, every 20 minutes, for years. It is one of the reasons a glass furnace can afford to stay lit for a decade. It recovers a huge fraction of its own waste heat and feeds it straight back in. But it is also one more system that has to keep working perfectly, continuously, for the whole campaign. One more thing that assumes the furnace is running and never stopping. And the length of time a furnace can run before that lining is worn out is called, exactly as in the metal furnaces, the campaign. For a glass furnace, a campaign is measured in years. A well-built, modern melting tank is designed to run continuously for something like 10 to 15 years before the refractory is worn thin enough that the whole thing has to be shut down and rebuilt. The very best push toward 20. Container glass furnaces, the ones making bottles and jars, often target around 10 years of non-stop operation, and across that entire decade, the furnace never cools. It runs day and night, through every holiday, through every shift change, through years of the outside world going by, because every cool down risks the glass freezing and every unplanned stop threatens to end the campaign early and kill the tank. That is the countdown the operators are protecting. A decade or more of continuous fire worth an enormous amount of money that can only be spent once, and that a single bad cooldown can cut short. And when the campaign does finally end, the rebuild is not a small job. Ending a campaign means letting the furnace cool in a slow, controlled way over days, tearing out the worn refractory and building the inside of the machine again from scratch. It is one of the largest and most expensive maintenance events a glass plant ever undertakes. For the years the furnace ran, though, keeping it lit was not stubbornness. It was the only sane choice. Now, there is one more thing glass does that metal does not, and it costs a fortune even when nothing goes wrong. It is color. A glass furnace does not make glass in the abstract. It makes a specific glass, clear, or green, or amber, or a particular tint for a particular customer. And because the furnace is a single continuous river with a decade's worth of glass flowing through it, you cannot simply switch from one color to the next. The entire volume of the tank, tons and tons of molten glass, has to gradually change over from the old color to the new one. That transition takes days, and during those days, everything coming out of the furnace is neither the old color nor the new one. It is a muddy in-between mixture that no one ordered and no one can sell, so it is thrown away. A color change on a large glass furnace can mean 3 to 4 days of producing waste glass around the clock, simply because the river is too big to change quickly and cannot be stopped to do it. So step back and look at the whole picture. This is a machine that cannot be turned off without dying. That cannot even be slowed too far without freezing itself solid from the corners in. That slowly eats its own walls on a 10 to 15-year clock it is desperate to protect. That throws away tons of perfectly good product just to keep moving, and days of product just to change color. Every instinct we have about machines, that off is safe, that stopping is rest, that waste is inverted inside this one building. And once you understand all of that, you understand why engineers reached for exactly this kind of machine to solve one of the most dangerous problems in the country. Because in that Washington desert I mentioned at the start, there is a place called Hanford. For decades during the Cold War, Hanford made plutonium for nuclear weapons, and the process left behind an inheritance that the United States has been struggling with ever since. Over 50 million gallons of high-level radioactive waste, a lethal chemical soup, stored in aging underground tanks near the Columbia River. Some of those tanks are more than half a century old, some have leaked, and the waste inside them will remain dangerous for longer than recorded human history has existed. You cannot store a liquid like that forever in steel tanks. It has to be locked into a form that will not leak, will not react, and will hold together for thousands upon thousands of years. And the form they chose is glass. The plan, called vitrification, is to mix the radioactive waste into molten glass and cast it into solid glass logs, sealed in steel canisters. Locked inside glass, the radioactive material is trapped in a stable, solid structure that water cannot easily leach out, that will not burn, that will not corrode, and that can safely outlast the danger of the waste itself. Glass, the ordinary material from your window, turns out to be one of the best long-term prisons for nuclear waste that humanity has found, and it is worth understanding why glass, specifically, and not something that sounds tougher. Your instinct might be concrete or steel or lead, something heavy and solid and obviously strong, but those materials all have a weakness for this particular job. Concrete cracks and is porous. Water can work its way in over centuries and carry the waste back out. Steel corrodes. Even very durable materials tend to have a structure, grains, layers, boundaries, and those boundaries are paths that water and time can exploit. Glass has almost none of that. On the inside, glass is disordered. Its atoms are locked in a frozen, jumbled arrangement with no neat crystal grid and no easy paths running through it. When you dissolve the waste into the molten glass and let it solidify, the radioactive atoms become part of that jumbled structure itself, chemically bonded into the network rather than just mixed in. To get them back out, water would have to dismantle the glass atom by atom, and glass resists that astonishingly well. We have natural glasses on Earth that have survived for millions of years. That is the promise. Lock the waste into a material that has already proven it can outlast almost anything, and the danger stays put long after the steel canister around it has rusted away. So the choice of glass is not a compromise. It is the whole point. And it means the furnace at Hanford is not just an industrial machine. It is the single tool standing between a lethal Cold War inheritance and the groundwater of an entire region, which is exactly why the rule that governs it is absolute. But to do it, you need a furnace, a melter. And this is where the whole story comes together. At Hanford, they built melters, massive machines, each weighing about 300 tons, running at around 2,100 degrees Fahrenheit. And into the molten glass inside them, they feed the radioactive waste. In late 2025, after years of delays and blown deadlines and locals who openly doubted the plant would ever run, one of these melters finally began turning real waste into solid glass. In its first stretch of operation, it vitrified its first 100,000 gallons. And that melter carries the same iron rule as every other glass furnace on Earth, only now the stakes are almost unimaginable. It can never be allowed to cool down. If the glass pool inside one of those 300-ton melters ever freezes solid, the entire unit is destroyed. Not repaired, destroyed. A 300-ton machine now packed with a frozen block of radioactive glass that cannot simply be reheated and cannot be easily taken apart because everything inside it is contaminated with the very waste it was built to contain. So think about what keep the furnace running means in that building. It is not about production targets or wasted product. It is about a machine full of nuclear waste that must be held molten continuously for as long as it takes to work through decades of Cold War poison, and where letting it go cold does not just cost money. It creates a new, enormous radioactive problem on top of the one you were trying to solve. And the scale of what that furnace is being asked to do is almost hard to hold in your head. The waste at Hanford is not measured in barrels. It is measured in tens of millions of gallons, sitting in more than 170 underground tanks, some of which were built in the 1940s and were never meant to last this long. The job of turning all of that into glass is not a project measured in months or even years. Realistic estimates for finishing the cleanup run for decades into the future, a task expected to outlast the careers of everyone who started it, and quite possibly their children's careers too. Every canister of vitrified waste is a slow, deliberate act. The melter takes the waste, blends it into the glass, and pours it into a steel container to cool into a solid log, then another, then another. Across the life of the program, the plan calls for thousands of these canisters, each one a small permanent tomb, each one requiring the melter to be hot and running and behaving exactly as designed. The furnace is not sprinting. It is settling in for one of the longest continuous industrial tasks the country has ever attempted, and the single thing that would end it prematurely, the one failure the whole design is built to avoid, is the glass going cold. Everything we said about an ordinary glass furnace, the no clean freezing point, the glass that welds itself into the tank, the corners that freeze first, the flow that must never stop, all of it is still true here. It is just that now the molten glass is laced with plutonium-era waste, and the machine is trying to bury one of the most dangerous substances ever made, one glowing log at a time, which brings us all the way back to the beginning, and to the strange fear that unites everyone who works around these machines. Picture the control room of one of these plants at 3 in the morning. Outside, everything is dark and quiet. Inside, the furnace is exactly as hot, as bright, as alive as it was at noon, because it has no notion of night. A small crew is on shift, and most of the time there is nothing dramatic happening, and that is precisely the goal. Their job is not to fight a crisis. Their job is to make sure the temperature never drifts, the flow never stalls, the reversals keep happening every 20 minutes, the glass keeps moving. They watch numbers on screens that to anyone else would look boringly steady, and they understand that the steadiness is the achievement. A flat line on those screens is a furnace that is still alive. They know what a drifting number would mean. A temperature sliding down. A flow slowing in the throat. The first cold corner beginning to set. They know that the death of one of these machines does not arrive as an explosion. It arrives as glass quietly getting thicker in a place no one can see, until the honey becomes tar and the tar becomes stone. So they hold the line, hour after hour, year after year, through a decade of nights, so that the fire never gets the chance to go out. We think of fire as the dangerous thing. Heat, molten material, a pool glowing at 2,000 degrees. That is what looks threatening. But in a glass furnace, the fire is the safe state. The fire is the flow, and the flow is life. As long as the glass is hot and moving, the machine is healthy. The walls survive, the campaign clock ticks forward, and even nuclear waste can be quietly, permanently locked away. It is the cold that kills. The moment the glass stops moving, the moment the temperature slips too far, the honey becomes tar, the tar becomes stone, and the stone fuses the machine shut from the inside. What every other machine treats as rest, this one treats as death. So they keep it running. In a bottle plant, for a decade at a time, throwing away tons of glass to protect a river that must never stop. In the Washington desert, holding a 300-ton pool of radioactive glass molten around the clock, because the alternative is a tomb that becomes a disaster. The furnace does not burn because someone keeps lighting it. It burns because everyone understands, with total clarity, what it would mean to ever let it go out.